So hello everybody, my name is John Hidders, Birkbeck College, University of London, and I'll be talking about the PG-Schema's paper our PG-Schema paper that was already mentioned by Alistair, and as most of you are probably aware, won the Industry Best Paper Award, of which we're really proud, so it bears repeating. And I'll sort of give a quick overview to give you some flavor of what went on in that paper and what we think are the main insights that we offered in that paper. The paper was actually the result of the working group that preceded the working group LEX that Alistair is chairing, the Property Graph Schema working group that I co-chaired, and there were quite a few people involved in that working group, most of which also ended up as an author of the paper. Here you see the list of authors and what they are connected to. So almost all of them are connected to LDBC. Many of them are connected to industry, many of them are connected to academia, some of them actually both, and some of them are also connected to actually the ISO organization, the WG3 working group that we are aiming to support. So we had a quite, I think, a nice spread of people with different backgrounds, which made the discussions extra worthwhile. I think one of the big contributions here is that we got people from with different backgrounds talking to each other and trying to come to a reasonable agreement about what schema language property graphs could or should look like. So, and I have to be honest here, we did an analysis of what we thought that people would be doing with schemas. And now the result of this is the overview that you see here, but this is a little bit reconstructed afterwards. The discussion was less clean, less straightforward than I'm going to represent it here. This is how we sort of summarized it and organized it afterwards in the paper. So the insight was that people probably are going to use schemas and actually already to some extent are using schemas for label property graphs in four manners. One is there is no schema, obviously, right? So for the blue column on the left side, where basically there is a schema. And then the second one is flexible schema, where there is a schema, but the schema simply dynamically adapts itself to whatever the users are creating. Right? So the schema does not restrict you in any way. Basically, its main functions descriptive. That means that it summarizes the data that you can find in the graphs. Right? It serves as a summary. The third column, we call partial schema, the third usage or type of usage, is where it's mixed in the sense that some part of the graphs that you're managing are flexible, are not restricted by a schema, and other parts are restricted by a schema. So there will be constraints, types specified, determine exactly what is possible, what's needed, but here, or to be valid on the schema and other parts of the graph, you're completely free, as it would have been as when the total graph was, or the total was flexible schema. And then on the right-hand side, the red column basically sort of a classical database setting, which is schema first, where before you can create anything in the graph, there will be a schema that completely determines what is possible and not possible in that graph, and restrict it in a very predictive manner. So our goal was to create schema language and sometimes to cater for all these types of users, right? Which is something quite a tall work. So what mainly really is being introduced that allow people to do this. So what you see here is just a diagram. This is not a schema language, just to give you an example. So we're trying to define here a schema that describes graphs as persons, note that represent persons, note that represent customers, which are a special case of persons, with edge here that indicate inheritance or subtype relationship, and there are notes that represent accounts, there are edges which indicate that a customer owns a certain account. And then there's properties indicated that in the green part of the box you see the labels. In this case, it's simple as only one label on the node which is the person, customer, or account. Right? So this is a straightforward schema. It's very UR-like people who have done it in the percentage. So we want somehow the equivalent for labeled property graphs that represents this. And so the basic idea that was not true to us when it existed, when we started basically, was that it was basically represented with node types and edge types, where a node type is the same. You see represented here, for example, for person, the blue bar represents the name of the type, which is a person underscore. Then there is a green bar, which is the label that has to be there on the node to be of that type. And in the curly braces, the properties are listed. Name and birthday, birthday is optional. that have to be associated with a notice be of that type. So you see also a customer type, and here you see already that the labels actually is a bit more complex. It's not possible in node types to actually have a so-called label extraction, which is really a combination of labels that allows you to say either it's label A or B, for example, or it must be label A and B or C, for example. So you can even engage, you can say it cannot have D, for example. So we took that also on board. That was not introduced by us. But what was introduced by us is the fact that here we can use the identifier of the type person in the place where you normally would write the label. So you could approach the way system focus are, let's say, a customer must have label customer and label person. And here you said, oh, anywhere you can write a label, you can actually also write name of type. And that means that all the labels of that type are included in this type. So a customer also has a label person, a customer also has a property name, and also optionally the property birth date. So that immediately gives you a way of specifying inheritance, right? So that's one principle. If you ever you could use a name, you can now use a type name, and that gives you inheritance. It also gives you that you can specify a union between the types of label expressions already allowed to express unions. We had to forbid this where there was negation. So under negation, you cannot do this, which is actually an open problem. We didn't manage to solve it completely in a satisfactory manner. And then finally, there's accounts, which is a name account, specifies the need of the label account, specified in green, and that has an ID.
Someone can fix the microphone.
They can't hear.
Okay.
Test. Can they hear me now? Testing 1, 2, 3. No, we've lost completely.
Oh yeah.
Good. Right. So the core of the schema would seem to be the enumeration of a list of node types specify what type of nodes are allowed. Now, of course, we also like to specify what edges are allowed, and for that purpose, edge types, which, as I said, already described in the abstract, simply consider a specification of which type of node is starting, what the properties and labels are on the edge itself, and what type of nodes are which we're in. And there, you can either, for the nodes, specify a complete node type, or you can just use an identifier as we're doing here as a sum, basically, which sort of in an obvious manner translates to the picture that we actually have here, right? You could take the textual notation straightforward and turn it into a graph, and it would extend it. So basically, the core of the schema would be an enumeration of node types and the edge types that are allowed, right? And the rule would be that a graph is valid under such a schema if every node has at least one node type to which it belongs every edge, at least one edge type to which it belongs. Now, of course, for schemas, you often also have some kind of constraints, at least constraints in the form of cardinality constraints and key constraints, for example. For that, we actually drew upon an earlier paper that we generated, the PG-Keys paper, that talked about specifying key constraints, but actually did so in a very general manner that was easily generalized to specify also other types of constraints. So here, some examples are given. For example, for a key constraint, you would first have a for clause that specifies the patterns where the key constraint applies. So this selects all nodes that are of the type account. And then you would specify that for that set of nodes, the eigen property should be a key. And actually, in principle, you could write here a complete query that constructs a tuple, and that tuple then should be unique for every account in this case. In this case, the tuple is just one value, right? So the notion of key, by the way, is actually, we found this out by looking at this closely, more complex than you might suspect, because the semantics is that the key value, 0.1, must exist, 0.2 must be unique, 0.3 must be identified. And those last two things are not exactly the same, right? Unique just says every account must have precisely one eigenvalue, but every eigenvalue must have precisely one account associated with it, right? And so a key specification specifies all of that together. Now you can generalize this by taking the first part that selects a part of your graph, a set of bindings, and have some other constraints like that another pattern must match, for example. So this says that for every node that is an account, I must be able to then match the pattern here where that account is fixed, and I must be able to embed this, which basically means that there must be an incoming owns edge from some customer node, right? And that then actually encodes here this lower bound. So that means that in that way, you can have a fairly simple textual notation to specify simple cardinality constraint. We didn't do this in the paper, but you can easily generalize this for, let's say, upper bound 5, lower bound 3, etc., or even more complex cardinality constraint. So a schema would consist of a combination of these things. So you have node types, edge types, and these extra constraints. That would be a graph type, which then could either be defined as strict or loose, and I will tell you in a minute what that exactly means. But this basically is a whole schema that you see right here. So what are the things that we sort of focused on and that we felt were important? One was that we wanted to have both conceptual and implementation efficiency, right? We had lots of theoreticians on board who were experts on this. And one way to achieve this was by being very strict in the hierarchy of the definitions that said that, well, at the bottom here we have the node types, or actually the content types, though we didn't introduce that notion in this paper. But so the node types are the lowest in the hierarchy, and the edge types are based on the node types that you defined, right? Because the edges have to hold between nodes that are there. Those nodes must be typed. So obviously, the edge types must use node types that already exist. And then on top of that, we would have the constraints that refer back to the node types and the edge types, because you can use those in the patterns that select where the constraints apply. And the information flow will always be in one direction, namely from node types to edge types to constraints. So it cannot be that, for example, because certain constraints do not hold, and suddenly that changes which edges belong to a certain type or not. And so that means that both for human beings and for the computer, the algorithms that do the validation, this has a low complexity. It's easy to understand for both computers and human beings. Also, we try to make it as compositional as possible, which meant here basically that we said, as I said, you can use types that you define that have an identifier consistently in other places by just using that particular identifier. And the meaning is that we can, or that if, for example, here we specify a node type, that in some sense you're taking here the intersection of everything that's being mentioned here. Or if you look here at customer, for example, we have here the Boolean expression. This is the AND operator. This is the OR operator. So that's interpreted as taking an intersection of two types and taking the union of two types. So if you know what it means to take the intersection of two types and the union of two types, you basically know what this means. So essentially what happens is that the identifiers, like person, company, and taxpayer, are replaced with the types that they represent, and then you compute the unions and intersections as specified. And that's the semantics of the type that is being specified here. So that's sort of fairly straightforward to formally specify and usually also to understand. We had to introduce the notion of abstract types to make this really work as most people would expect who are used to ER modeling, for example, because that allows you to specify here this node type taxpayer, but you don't want nodes that are just taxpayer. If somebody's a taxpayer, they must be either a person or a company, and that's what the keyword abstract here actually accomplishes. So if you put abstract in front of it, that means you're defining a type that can be reused to build other types. By itself does not justify the existence of a node or an edge. We also have abstract edge type. So in that sense, we have compositionality. For the different use cases that we had in mind, we also introduced the notion of strict and loose schemas. So a strict schema basically is a schema that you would expect in a, let's say, a classical database setting where the schema strictly controls what is possible and not. And the interpretation of this is as follows. If the schema is strict, that means that we have the rule that every node and edge must be of at least one type in your schema. So every node must belong to at least one of these node types here, and every edge must belong to at least one edge type here. And of course, these constraints must also be satisfied, right? So that's sort of a quite restrictive schema, hence the strict keyword, as opposed to the schema being loose, which means that we now drop the requirement that edges and nodes must be covered by one of the types here. That means you can also have other edges and nodes, that's fine, but you do need to satisfy the constraints, right? And note that these constraints still need the information whether something belongs to a type or not. This only applies to account nodes, so there must be a type account, and so this determines when you belong to a node, to a type count or not, right? So the types still need to be there, but they're no longer the factor that restricts what is allowed in your property graph or not, right? And so that gives you then indeed sort of some restrictive power that you want, but to some extent also are fairly permissive in what is allowed in the graph and what is not allowed in the graph. On top of that, we also wanted to have flows of open types, which simply meant that, maybe this wasn't clear already, but the types as they were specified now were closed in the sense that the set of labels that was allowed and the set of properties was allowed was exactly the set of labels and properties was allowed. So there could not be additional labels or additional properties. If you don't want that, if you want to say actually only if you want to say that the properties and the labels that are specified are just a lower bound, so that's what must be there if you want to be of that type, but others can be added as well, then you should declare this open. And it occurred to us that it's even probably interesting to allow it to be open in the labels, so you can put the open keyword here. So this means it has at least the label person and maybe other labels. That's up to the user. But the properties here don't have the open keyword, so that's closed. So only those two properties that I mentioned there are allowed, right? So you must have the name property, the property name, and you can have the property birthday, but it might also be missing because it's optional. If you want to make it open, the properties, you can do that too. So you can put the open keyword there as well, and then actually also the properties are open, and you can have additional properties. Okay, so that was actually the basis of it. So I hope you sort of agree that this is not too difficult, but it's fairly straightforward. But as a combination, it's actually quite powerful and does seem to cover most of the use cases that we had in mind when we wrote the paper and when we were discussing this in the working. That's kind of the point, that it's a simple model that is hitting a nice, sweet spot that is quite effective. Of course, we did more to deserve the Best Paper Award. We did a fairly thorough analysis of what the formal data models, existing systems, etc., all were doing at the moment of writing in terms of what the schema language can and cannot do, which was, to be completely honest, a little bit all over the place in the sense that many different systems had quite different and distinct ideas about what the schema language should be doing and what not should be doing, although there were sort of some general observations, and roughly speaking, we did sort of cover most of the stuff that most of the existing systems, for example, were offering, right? Formalisms, the theoretical data models, for example, tend to be quite rich, and so we did not cover stuff. We introduced a full grammar that was specified actually and even implemented. There's an implementation that you can play with, so there's no semantics behind it, you can do parsing. There's a formal semantics, which was not easy, although the complexity of the schema language is not, say, that high. It did require quite some work, for example, to exactly specify what the union of two node types and the intersection of two node types and for edge types, the same what is the union intersection of those things is exactly. But once that's defined, almost everything else, the semantics of the schema language follows from that. And so we compared it also with all the existing formalisms, not exactly, so there's no theorems in the paper that say this is more expressive or less expressive, but there is an informal discussion of how things compare to each other. And of course, we discuss, especially concerning the constraint language, but also the things that Alistair mentioned, some of those, we already briefly sort of hinted at what we think those extensions could look like. Okay, so what were sort of the main lessons that we think we learned? So we think that we sort of hit a nice sweet spot here in terms of simplicity that is implementable and but covers most of the use cases that we sort of encountered here. Also, what is interesting, because we had a very diverse group of people with different backgrounds, and this was quite difficult to sort of reach, didn't reach a complete consensus, but sort of enough to write this paper, which was quite an achievement, I think, certainly looking back. And so that's in some sense the main contribution, I think, that we got that many people, such a diverse group to agree on most of this stuff. But there's certainly a lot of open problems here, things that you might never expect. For example, things like negation and recursion, we have not resolved fully. So we don't know really what it means if you have in this label expression, right, where you could say it's a person and an engineer, for example, or it's a person or an engineer or a manager. What if it says you're not an engineer in the type, And that engineer happens to be not just a label, but actually a type identifier, and so refers to a complex type. We don't know exactly what it means, or at least we don't know of a meaning that nicely corresponds to an intuitive semantics that allows you to easily reason over these things. For example, for the Boolean type expressions, if you have union and intersection and also negation, you would expect that it behaves like a Boolean algebra. But we never really define or were able to define an intuitive semantics that really is Boolean algebra. So there are quite some, let's say, not so obvious, interesting challenges. There are still also recursive types. Also, one of the things that's still open and actually quite important, or at least by a big part of the group felt as something important, is to have a representation of the schema as a graph, right? So I completely agree with Ora there. That's absolutely essential. But it is a bit of a challenge in the sense that these type specifications, for example, you have these Boolean expressions. How do you represent a Boolean expression as a graph, right? What is the most intuitive way of doing that? Such that it still sort of looks like a graph that you would expect if you're somebody who's used to ER modeling, for example. So that's not so, at least we felt this was not so obvious at the moment. So there are plenty of challenges left here, actually, in addition to all the challenges that Alistair actually already mentioned, because all those things are also, certainly far from trivial and under discussion. And that's actually what I want to tell to you today.
Thank you. Over many questions. Okay. Where do we start? Giacomo was first, I believe.
Okay, thank you. So one quick question related to the subtyping that you provided, because as far as I'm concerned, the symbol was an at and an at. So that might entail that maybe the intended meaning is not like in type theory, less two dots, rather like a product between two types. So is that the case, or is that actual subtyping like in type theory?
It's actual subtyping like in type theory. So the and symbol should be read here as taking the intersection of two types. So it's an intersection type in the sense of being the counterpart of a union type, right? And so this is the type. This is the type of intersection type where if you take two records with field A and B and field B and C, and you take the intersection, you get a record with fields A, B, and C, right? And that's exactly that is the exact counterpart of subtyping, right? Because type 1 is a subtype of type 2 if the intersection of type 1 and type 2 is equal to type 1. So
that makes also the type inference decidable then as a consequence.
Oh yeah, this is all very decidable. So reasoning is very easy. I mean, the thing that makes reasoning hard is actually these constraints, right? But there the theoreticians are very happy about it. You can invent all kinds of subsets of this that are still decidable and things like that. But so that part above the line here is very easy to reason about.
Okay, thank you.
I see that, first of all, you kind of went for a declarative approach for the language on the contrary of what you have in relational languages where you have create table and then create column, and I think that's a great choice. But how do you do mutation of your types? Say, I want to remove a field, add a field, and that could be simple because you just redefine it. But what if I want to just change the name of a type or a field?
Okay, so that's the thing that's still under discussion. But having said that, I don't think there's a deep problem there, to be completely honest. I mean, it's trivial, for example, adding a type or removing a type, sort of it's obvious how to do this and what kind of consequences this has, or even updating a type, right? If you have a certain node type that has a certain name and you want to replace it with another node type, maybe with the same name, well, that's removing the thing and then adding it. But the complexity, of course, I think, is mostly here in the question of if somebody specifies an update like that to the schema, what is the sort of the extension of the update language that allows you then also to specify how the data is updated so it fits the new schema. And that's the real challenge that we did not think about at all. So updating the schema is not a problem, but updating the schema in a way such that you automatically update the data to fit the new schema, that is the real challenge. And because that, in some sense, The whole subproblem would be finding sort of a mini transformation language that is typed, etc. And the whole typing problem is a big open problem at all, right? So if you have a query and you have a schema, is the query well typed or not? Can I predict the output of the query in terms of type, etc.? That's all open. The only thing that we can say right now, at least we now have formally defined what the schema language looks like, so we can now start research, but we haven't done so yet.
Thank you.
So I have a comment and a question. So as far as I know, the visualization of these class expressions as a graph that's actually readable to users is still a kind of an unsolved problem. My question is about negation. So does the lack of negation means that you cannot define things that are disjoint? Sort of like that are disjoint.
Disjoint, okay.
So if I wanted to like have a node type like animal and then subtypes of cat and dog, I might want to be able to define that cats can't also be dogs.
Well, that's true, but also a little bit untrue, because first of all, because the types act like, that's by the way where we probably conflict with your view. So the types are really sort of data structured types. So the node types, they specify I have properties A and B, then that's exactly the properties that you must have. You cannot have property C. So they're closed in that sense, right? In a conceptual data model, that I think would be different, probably. We just say, well, it means it has at least A and B, and maybe also other properties. The type specifies an upper bound, so to speak. But because it works that way, these closed types tend to be disjoint because of that semantics, sort of unintentionally, you might almost say, but that depends on what you're exactly doing. So in that sense, you have a little bit of power to sometimes introduce disjointness. Secondly, because we have this constrained language, you can specify disjointness there. You can say if something is of this type, then it cannot be of the other types. So I wasn't clear about this, but in these patterns, for example, you can have negation, and under the negation, you can actually have the type identifiers. So there you can compensate this. So you can express this, except, and that's annoying, it now ends up in the part for which we know that reasoning is actually quite hard, right? We ideally would like to have it here. And so that's why we started looking at this, and that's also why we think that that's an interesting problem that we still would like to try to solve. If we can get it there, probably it ends up in the part that's easy to reason about rather than the part that is hard to reason about. So you sort of can express it if you want, basically. It's just not in the sort of the happy place that we want it to be.
By reasoning, you mean consistency checking?
All of it. Consistency checking, but also the typing problem, the problem of I have the graph transformation, and I know that the input has a certain type. Can I guarantee that the output has a certain type? Can I determine if the query is well typed or not? Can I decide if the result of the query is always empty under this schema? All that kind of stuff, right? So just, yes, reasoning about consistency and just the schema itself, but also about the combination of the schema and the query expression, which is also reasoning, right? But usually a bit harder than just reasoning about the schema, actually, which is also a completely open problem. This typing problem, actually, I and some other people already wrote sort of a small paper in POTS this year about this, but it's very small in the sense that we looked at a really tiny sub-fragment of this schema language and a very simple graph transformation language. But so there's lots of work to do there, for example.
So if you are already suffering from the implicit disjointness, which is a form of negation, why not just have explicit disjointness? Why not just say person is never a car explicitly? You already have it, right? By having this by default disjointness. If you don't have this open,
Right.
It means things are disjoint.
Yeah.
Right?
So
why not explicitly
state? You have to closed types that actually do overlap, but that's sort of artificial. It's sort of a theoretical. There's sort of a corner case where this is possible. Usually they're disjoint, yes. For example, because we have optional fields, right? You can define a node type that says you have property A and B, and the other type says you have property A and optionally property B. So those two types overlap, right? But they're closed. They have an upper. So
Yeah, I'm just going to comment on the schema graph issue. I mean, I think that I already sort of presented this. I think you have to have a dual structure. You have to separate the type, the record type system at the lattice from the actual graph representation and show the mapping between them. And then you can handle the complexity. You keep the simplicity of the visualization. Okay.
So we are a bit over time, and I propose to move Max's talk to the next session.